Close your eyes. Now imagine everything that makes you you, your memories, capabilities, your favorite song, your child's laugh, or even how to take one step forward are slipping away from you. That's terrible, right? But for millions of people across the globe struggling with either Alzheimer's or Parkinson's, that's not imagination. That's the daily life. And these conditions not only impact their minds, but slowly steals away their connection, identity, and independence. So we have to find a way to fight back. Unfortunately, the human brain is one of the most complex and the least understood systems in existence. At its core are neurotransmitters, small molecules that take messages to different parts of the brain. And the irregularities in their concentration in the brain bring about neurological conditions. But our ability to monitor these neurotransmitters in the brain is very limited. The current diagnostic tools, such as MRI imaging, are very insufficient and expensive. They require patients to go to specialized facilities only to offer snapshots of how their brain is behaving at that moment, which leaves big gaps in our understanding of how dynamic brain chemistry can be. But now, what if we could move past these limitations? Imagine an implantable chip, a flexible, tiny sensor that could go into a patient's brain and monitor the neurotransmitter levels in real time. So it would be selective, sensitive, and accurate in detecting neurotransmitters like dopamine and glutamate, even in complex biological mediums. Much like a glucose monitoring sensor, it will give us real-time data, which would enable doctors to know the patterns and take action more effectively and timely. So in my group, we are trying to build that chip. We have been testing with different methods. We are doing electrochemical sensors, and we've been testing with different carbon materials as the platform, which will be modified with metallic nanoparticles. These metallic nanoparticles have different structures and configurations, and they would be sensitive to certain degrees to different neurotransmitters. So our most optimum platform yet is very sensitive towards dopamine and the subproduct of glutamate. But interestingly, it's very insensitive towards the usual interference in the brain. But functionality is not the only goal we are pursuing in this study. We have three more. One of them is biocompatibility. So the reason we chose carbon as the platform is that it would be kind of easy to plant these sensors in a biological medium and hope for long implantation time. Also, the neurotransmitters that we have fabricated have shown low toxicity levels towards cells recently in preliminary tests, which means that cells will stay alive if these nanoparticles are surrounding them. The second one is sustainability. So our nanoparticles are made out of precious metals, gold and platinum. So we have decreased the amount of needed metals by working with nanomaterials, and as well as enhancing the electrochemical sensing performance by having higher surface area. And the last one is scalability. So MRI machines are not scalable. They cannot be manufactured like for every household, but these sensors have the ability to be deployed in high numbers for people who would be needing them. So bottom line, this technology can be breakthrough. It will, if it actually goes to its final destination, it will provide personalized care, gives us better understanding of the brain, cut the costs of healthcare. But like the most important thing that it can do is that it will let your dear ones hold on to the most dearest moments of their lives. And that's not a small thing. It's tough, but it's not impossible. And which kind of gets me to this slide. Like all good research, this research needs collaboration. And I invite researchers, clinicians, and supporters to reach out to us and collaborate with us so we can make this vision a reality. Thank you very much. My name is Bahar Mostafiz, and thank you for listening to me.